Great. So yeah, thanks so much for the opportunity to be here. I'm going to be talking broadly about an applied econometric perspective on large language models. And the style of this talk is going to be sort of a little bit different than a usual talk in economics. So rather than really just focusing on one paper, I want to provide sort of a brief overview of a series of papers on large language models that I've worked on with a team of co-authors spanning economics and computer science, and then hopefully explain why I think this work is relevant to what we do every day. So, I think as a starting point, it's a bit trite to say this, at the end of 2025, but large language models are really, truly amazing pieces of algorithms. And in particular, for applied researchers in economics, they have drastically lowered the cost of analyzing text for applied work. So as a result, it really feels like over the last 2 years, applied researchers' creativity has been unleashed. And I think we're really starting to see a lot of exciting work come out. So just to give you a few examples, what is a question that would now be very straightforward to tackle? In finance, we might want to ask, is the market using tacit information to sort of price, price equities after earnings calls? And now we might answer this question by just prompting a large language models to try to predict stock returns from transcripts based on these earnings calls. In political economy, we might be interested in understanding what is the effect of some local policy change on partisanship. Well, now it might be very straightforward to go and collect a large data set of social media posts, prompt a large language model to label those posts for partisan identity, and then stick that measure into a diff and diff or an IV style regression. And then perhaps a little more out there, there's been really interesting work trying to use large language models to make new insights about people. We might prompt a large language model to simulate the behavior of human subjects, what people might call in silico subjects, in various experimental conditions, in order to draw new conclusions or generate hypotheses about how people might behave. So across all of these applications, what I want to think about over the next hour is quite simply, people come to me all the time and ask, what sort of econometric guidance can be given to help applied researchers use large language models in exactly these sorts of research questions. In thinking about that problem, there are several sub-questions there. Will inferences be valid if researchers just pop in a large language model output into their usual empirical workflow? Will their standard errors be correct? Do they somehow have to adjust their estimation strategy because they are plugging in these outputs into downstream research? And I think the core challenge in answering this question is that large language models themselves are extremely complex, constantly evolving, and multifaceted algorithms. So as a result, when we try to think about building an econometric framework for using large language models to answer empirical questions, we have to do so with a degree of humility, without mistakenly making high-level assumptions about intractable problems in computer science and machine learning. So what I'm going to do towards the last 30 minutes of the talk is I want to lay out an applied econometric framework that can help guide empirical research using large language model outputs. And in particular, I want to emphasize that the specific guidance that I'm going to be providing is going to depend on what is the specific use case of the large language model for the problem at hand. And in particular, I'm going to distinguish between two types of empirical exercises. The first are what we might call prediction problems, in which we link some observed economic variable to some pieces of text, and we just like to predict that economic variable using the text or embeddings based on the text. The second are going to be what we'll call estimation problems, in which we think that piece of text expresses some economic concept that we would like to measure. And if we had those measurements, we would simply plug them into various downstream regressions or quasi-experimental designs that we might be interested in. And while those two cases might seem very simple, I'm going to then argue that understanding these familiar uses will help provide guidance or some clarity around more novel use cases of large language models, such as using them as tools for hypothesis generation or human subject simulation. So to dive in, let me just start introducing a little bit more structure around these prediction problems and estimation problems, and then I want to talk about some recent work in computer science. So in a prediction problem, let's imagine that a researcher collects some text pieces that I'm going to denote by R, and they want to use that text piece in order to predict some linked economic outcome YR. So as a running example that you can keep in the back of your mind, so imagine the text piece is some financial news headline about a particular company, and the economic outcome is the realized return of the equity associated with that company within some window around the headline's publication date. So for example, one headline might be that Bank of New York Mellon's Q1 earnings per share missed its estimate from Wall Street. So given this sort of data, a researcher might use a large language model that I'm going to denote throughout by this M hat object, and I'll explain this in notation a little more later on, in order to form predictions about this economic outcome Y hat. These predictions could be generated perhaps by directly prompting a large language model, perhaps with some few shot examples, or by taking a large language model's pre-trained embedding and fine-tuning it using some supervised learner. Regardless of how these predictions are generated, the researcher is then going to calculate the large language model's sample average loss on their collected data set. And what they would like to know is, can we use this calculation to draw conclusions about how well this outcome can be predicted using these text pieces? Next, what do I mean by an estimation problem? In an estimation problem, we're going to start in a very similar way. The researcher collects, again, some text pieces R and links those text pieces to some observed covariates WR. Importantly, we believe that these text pieces express some economic concept, VR, that would be costly to collect and is defined by some existing measurement technology. Now, this measurement technology is going to be something that will always be lurking in the background. It's implicitly chosen by the researcher, and it captures whatever the researcher would have been satisfied to use absent using large language models. Ultimately, I think the most credible form of a measurement technology for using text is the researcher themselves. If the researcher does not believe that they could read these text pieces and label this economic concept themselves, I would argue this is a very ill-posed empirical exercise. So we're going to take the existence of this object as given. So it's
Just a
something to put
question
in the
about
back of
that
your mind.
point.
Yep, sorry,
Yeah,
Dean, go
just a
ahead.
question about that point. I mean, sort of thinking about, LLMs as just maybe scaling up something that, hey, the research
Yep,
team could do, versus
yep.
sometimes people might imagine one of the things that an LLM could help me do is measure this in a language that no one on the research team speaks. But somehow we're kind of imagining that, if we did have native speakers in all these different languages that the text is available in, we could measure it, but no one on the team is able to actually do that.
So again, that's why I'm going to be a little bit agnostic about what specifically is the measurement technology, because I think the choice of that really depends on the context. So I think, in this example, I'm going to talk about where the text pieces are pieces of congressional legislation, the concept is the policy topic, the expressed by that legislation. There the measurement technology is naturally, if you have some political scientist or group of political scientists on the team, do you believe that if they were to get together and read these documents, they could produce that policy topic? Another context it might be, maybe it's in a different language. Do you believe there is some expert who speaks that language? If they were to read these documents, they would produce a label, and you would be satisfied to use that label if it could be scaled across the corpus. I think another thing you're hinting at, which I'm going to talk a bit about at the end, is what if that is just impossible? There is no way of collecting some what I'm going to call validation data later on. Can we still do something? And I'll talk about that at the end. So, exactly as Dean was alluding to, the way we're going to think about these estimation problems is, if this technology could be applied on all documents or text pieces in the corpus, the researcher would simply take those resulting labels and plug them into some downstream regression and say, report the coefficient on these covariates WR.
Uh,
So in that
Ashish,
sense,
can the
yeah.
economic concept be heterogeneous across different labeler or customers? For example, if we're thinking about advertising text and different people, when they are seeing it, they have different kind of like preference or reaction.
Good. So again, there I'd say that the core challenge sort of for thinking about, what is exactly this VR would be, in the context you're describing, perhaps this VR is an advertisement that has some text. I would like to know, does the customer like this text or not? And so in that sense, I would think about, I have to augment the notation a little bit to think about V being indexed by both the customer and the text piece. And so there, VR would be what would the customer's elicited preference or, how much they like this ad be if it were presented to them. And a lot of the arguments are still going to go through, assuming we have access to the ability to collect some small amount of validation data. And then again, there's a natural question. Maybe if we don't believe we can do that collection, could we just somehow still use the large language model anyways? And we'll come back to that at the end. So all to say, what the researcher hopes to use a large language model for in these estimation problems, as Dean and George alluded to, is basically as solving a text processing problem. They do not believe they can scale their measurement technology across the full corpus, so instead they're going to use a large language model to produce some v-hats and then plug it into this regression and report what I'll call beta tilde LLM. So then the question for an estimation problem is, does beta tilde LLM actually recover beta star, the object we're interested in? Now, ultimately taking a step back to make sense of the use of large language models in empirical questions like this, we have to make sense of how good are LLM outputs for these prediction problems, predictions of Y, or producing measures of the concepts we're interested in. So ultimately, this becomes a question of how should economists approach this question in the world of large language models? Well, a natural starting point would be to ask, how does the field of computer science and machine learning and AI approach this question? So I want to spend some time talking about that now. Now, broadly speaking, the quantitative basis for the performance of large language models largely arises from what are often called benchmark evaluations that measure how well large language models perform on a particular collection of queries and questions. So, for example, one type of benchmark evaluation that you've probably heard of 2 years ago were popular evaluations of large language models on standardized exams like the GRE, the SAT, or AP exams. But perhaps the most important types of benchmark evaluations in AI include questions or queries aimed to test what people call a model's quote unquote general intelligence. So, for example, one popular benchmark for testing the general intelligence of large language models is known as HelloSwag, and it includes questions to test how well models perform on common sense reasoning tasks, such as this. Suppose a woman is outside with a bucket and a dog. The dog is running around trying to avoid a bath. And then there are multiple choices, and we want to know, does the large language model logically complete this story? Other sorts of benchmarks, one popular one is known as Big Bench Hard, which examines model performance on harder reasoning problems that involve multiple steps of reasonings. So one example of a question in Big Bench Hard is, if you follow these instructions, do you return to the starting point, turn left, turn right, take 5 steps, take 4 steps, turn around, and take 9 steps? And we want to know, does the large language model answer this question correctly or not? And of course, as these benchmarks have become quote unquote saturated, we think models have been trained on them, new sorts of benchmarks have been developed and used, such as more domain-specific ones related to mathematical reasoning, coding performance, and PhD level science questions. So in order to understand how we might use large language models, ultimately, we're going to have to evaluate the quality of large language model outputs. Much of the computer science world approaches this question with benchmark evaluations. So then our problem becomes, what exactly can we as economists infer from exactly these sorts of benchmark evaluations? So what would be 2 ways of approaching this question? Well, putting aside their, stochastic nature and their exact implementation, let me just put forth 2 stylized views of large language models that I find clarifying for myself, and then we'll walk through whether this is satisfying or not. So one stylized view of a large language model is, well, it's nothing more than an arbitrary mapping that's going to take in queries or prompts and produce responses. In this view, provided we believe that the benchmark evaluation was some held out set of queries that the model has not been trained on, and the benchmark has been sampled from some underlying distribution of queries or tasks that large language models might encounter when deployed in the world, what we're learning from these benchmarks is effectively an estimate of the average performance on the large language model on this sampling distribution over queries and tasks. Importantly, this first perspective is exactly the perspective we took circa 10 years ago in deep learning and supervised learning. So, for example, in image classification, this is how we would interpret performance evaluations on, say, ImageNet. Now, is this a satisfying perspective for large language models and how we how we hope to use them in applied research? Well, I would argue no. If we tried to articulate what exactly is the sampling distribution over queries encapsulated by these benchmark evaluations, they would appear to be far removed from the empirical use cases we began with. They're not about labeling the policy topics of congressional bills or labeling the partisan slant. They are more trying to evaluate common sense reasoning or quote unquote general intelligence. So, in other words, if you want to go down this view, you have to ask yourself, do you really want to be deploying large language models on the types of questions that are seen in these benchmarks? And I would then encourage you to go and actually look at what questions are in these benchmark evaluations.
Ashish, can I ask a clarification question?
Yeah,
I mean, aren't the evaluations though just just a function of what the evaluator wants to evaluate the language model on? Like the distribution P could be way more general than the lens of the evaluation mechanisms that we place on them, right?
absolutely. Absolutely. So I think all I'm trying to articulate here is if you took this more supervised learning perspective on what we get from a benchmark, you have to confront there is this seemingly mismatch between what are the types of questions in these benchmarks and where we seek to use them. I would argue that's a too narrow of a perspective. When we evaluate, say, a person on the SAT, the GRE, or PhD level science questions, surely we're drawing more general inferences about their abilities across a wide variety of tasks, not just the types of questions that are in those exams. So that's exactly what I want to go to next. So that would be one stylized view of thinking about a large language model. I think that's not fully satisfying. After all, large language models are not just arbitrary mappings from queries to responses, but instead, it feels like we approach them much more like they are a bit of a brain in the box. That because of all their pre-training, fine-tuning, and RL steps, large language models, they're not perfect, but perhaps they understand and misunderstand the world like we do, or perhaps like the smartest person you know. So in this perspective, one might very roughly view that really benchmarks are a curated set of queries designed to try to evaluate this claim. And in other words, if we saw good performance on a benchmark, we should be more confident that large language models perhaps perform as well as the best possible human or something outside of the human frontier. So what I next want to do is I want to talk about sort of two streams of papers that we've worked on, published in computer science venues, to try to make progress on formalizing what this perspective might be and how would we actually assess whether this is actually happening. And then I want to come back to this original question of what exactly can economists infer from these benchmark evaluations.
And just to kind of ask what
Yeah.
the upshot of this is going to be. I mean, one way, if we stuck in this arbitrary mapping view, would be to say, look, we need to create our own problem-specific benchmark. This is kind of, in some ways, you might think of this is what people already do when they have human raters. They do things like compute inter-rater reliability. So we should do that kind of benchmarking, and then we should use, prediction-powered inference or design-based supervised learning. And so I guess maybe one of the answers to the question is like, is this going to allow me to the end get smaller standard errors than if I used PPI or DSL? Or is it, how confident can I be in then just not collecting that kind of data? Is that how
Yeah,
you sort of think about this?
fantastic. I would say, how is this going to fit into where we're going to go? Is when we reach for large language models to apply them in some implied question, we're effectively taking a big leap of generalization off of benchmarks. Sort of benchmarks typically don't contain the problems we want to use them on, and we're drawing some inference about because the large language model gets a gold medal on IMO, it can solve this task that I'm going to deploy it on. And I think one message coming out of sort of this work, but really a broader literature in computer science, is that generalizing off of benchmarks is very difficult. And typically benchmark performance provides very little guidance of performance off of benchmarks. So if we can't take these benchmarks at face value, what should we do when we try to apply large language models in our own work? And one version, exactly as you're saying, Dean, is we need to start thinking about first designing perhaps benchmarks that look closer to the types of problems that we work on. You see this within, for example, AI for medicine. What would a benchmark look like in, say, political science, political economy applications, marketing applications? But then in any specific problem, you should interpret the collection of validation data as effectively creating a problem-specific benchmark. And then how can we use that to reliably get good downstream inferences? So I think, exactly what you said is where I want to go. But first, I want to bring everyone onto the same page and sort of realize there is this mismatch between what we know about large language models in the world and how we want to use them in our problems.
Uh, Ashish, for evaluation and generalizability, like how should we think about this versus like, let's say program evaluation, evaluating a convenient sample of experiments or A/B test that we done, like we derive a certain result and we are hoping to kind of generalize the results to other contexts, even though sometimes the out of distribution test is not like perfectly, like we don't know how to do that.
Yeah, I think that's a great analogy. So just to restate it, when we're doing program evaluation, we're doing an A/B test. Uh, our view of the problem is we might be, say, either randomly sampling or randomly sampling with some weights, units to enter into our experiment. And then once we randomize, we're confident we're getting internally valid estimates for the average treatment effect from subjects drawn from the population we are sampling in. The question you always face is, well, what happens if I tried to take that estimate and port it to some other population, some other treatment? This is the problem of external validity. And in a way, the challenge, exactly what I'm going to articulate with large language model benchmarks, is exactly that same problem. Except it becomes a little more challenging, I think, to even conceptualize, what does it mean to be randomly sampling tasks to assess general intelligence? What does it even mean to be randomly sampling problems to assess PhD level intelligence? In other words, in our world of program evaluation, we have sort of a clear view of what sort of the in-sample distribution P is. And we know if we deploy it to some other distribution Q, we have a sense of talking about distribution shift, and we can assign labels to different types of distribution shifts. Here, I'd say we face a very similar problem, but one that's even harder to articulate. It's not really clear that I would use the same language as covariate shift, label shift, et cetera. But that's exactly the right intuition.
See, I have the exact opposite reaction, which is that this seems so much easier than issues of covariate shift in program evaluation. There, it's like there's this whole, hypothetical universe of possible interventions and all these things that are unobserved. Here, a lot of the use cases are like, can't I sample some of the examples and label them myself and get the ground truth? And it seems
Oh,
like I
good.
often have the distribution of exactly what I need
Good.
processed. And so to
Good.
me, it
I
seems like
think
actually a much easier case.
no, so let me now sort of try to distinguish between the activity going on in the construction of sort of general purpose benchmarks versus what you have in mind, Dean, which is, I am the researcher, I have a corpus of documents. Let me just randomly sample some of those documents to collect labels on.
Mm-hmm.
And I would say when you're in this world of sort of general purpose evaluations, as I'll talk about, in a couple of slides, uh, one general finding we have is if you show that a large language model performs well on some task A, there's often some adjacent task A prime on which it's going to perform very poorly. Now, you still have learned that it performs well on A because I've evaluated it on A. And I think that's the analog of the world sort of you have in mind, which I think is the world we should be operating in for particular problems. But these are fantastic questions, and they're previewing a lot of stuff that I hope will come soon. So let me just talk through this first paper where one view of large language models is that they think like people. Consequently, even if they're not always correct, their errors are going to be predictable to us ex ante. So in some work with Kian Vafa, who's on the job market in computer science this year, and Sendham Malainathan, we set out to try to evaluate exactly this sort of what we call anthropomorphic generalization of large language models. So how did we do this? What we did was we first elicited a large data set of what we call human generalizations. So we presented subjects with a large language model, some question, and the large language model's answer on that question, and whether it got that question right or wrong. And then we showed the same subjects another question and asked them, do you believe the large language model will get that question correct or wrong? So just to give you some examples of problems we showed people, we presented people, for example, with a type of logic puzzle that you would see on the LSAT about Alice, Bob, and Claire playing a game. And then if they were told that a model got that question wrong, they updated their belief that the model would likely get a similar type of logic question wrong as well. And we also did questions in biology, some questions just about unrelated questions about calendar time and whether you know something about Pepto-Bismol, and so on.
Can I ask a question about how you think about task similarity?
Yeah.
How do we define that tasks A and A prime are fundamentally similar?
Great question. Can I hold on that for like 1 or 2 slides? Because I'm going to show you some evidence, and then making sense of exactly what it means for tasks to be similar or not is where the literature is now. Yeah. And then once we elicited this data on human generalizations, we then just contrasted human predictions about large language model performance with observed performance on these question pairs. And what we found was that large language models, on the families that we studied back in 2024, this been recent work sort of showing pretty similar results on more modern models as well. But we basically found that large language models appear to be systematically misaligned with human generalizations about correctness given observed performance. So we were looking at the llama family in 2024. You could ask llama, say, questions about the marginal propensity to consume. It would get it right, but it would fail basic arithmetic problems. It would get questions about logic correct, but get sort of small modifications of those logic puzzles wrong, and so on. And furthermore, we could have people play this same game with other subjects in the experiment. And it turns out subjects are very good at generalizing the performance of other people, but they're actually quite bad at generalizing the performance of large language models, and scale did not appear to fix this problem. Language models with more parameters, larger training sets, did not appear to be easier to generalize. And so we interpret this as sort of evidence of a type of anthropomorphic bias in how people use large language models. And now coming to Olivia's question, this is now sits in a larger literature trying to document this problem, showing that people are very bad at generalizing performance to new tasks based on observed performance on existing tasks. And so some ways in which people have thought about, what does task similarity mean is these are 2 grad students at Harvard last year. They have a very nice paper trying to construct measures of sort of what a human believes a harder question or not is. So within a domain, think about if you could answer a simple biology question correctly, that it does not imply you can answer a harder biology question correctly, but the converse is true, and show that this is a common error in large language models. And then some recent work tries to formalize the idea of what you might call a Potemkin, or what the authors call a Potemkin, where the idea is a large language model can provide the definition of a concept, but when presented with examples and asked to label whether this example exhibits that concept, it often breaks down. So sort of trying to reverse the structure of a question as well. But more broadly, what sort of the messages coming out of this broader literature is what you might have heard about this sort of jagged frontier. The jagged frontier of large language models is simultaneously a statement about model capabilities, what we are evaluating them on benchmarks, and our ability to forecast performance on new unseen tasks, something that we appear to struggle with. So in other words, it's very difficult, at least now, to generalize performance from benchmarks using just our intuitions. A common intuition people have is that, well, if a person could do A, then surely so could a large language model. At least so far, that doesn't appear to be reliably true.
Ashish, a question about the previous slide. So do you observe both, or overestimation of the model's capability to generalize and an underestimation in the sense that humans think that the model is not going to do well on a task, but it actually does well?
Yeah, I think we provide a bit more discussion of this in the paper. And if I remember correctly, but again, refer you to the paper to get the specific details, is most often the structure is of the form a person sees an LLM gets a question correct. They've updated their beliefs about performance, so they think the large language model is going to be correct on some adjacent problem, but then it ends up being wrong. And so oftentimes there's sort of a related line of work in CS that sort of talks about the brittleness of large language models, that you can often sort of adversarially construct tasks that look similar to A, but they will fail on. So one of the earliest versions of this people might know is this really nice paper on what's called the reversal curse, but which is a very specific example that's been sort of since generalized.
Thank you.
So now that sort of treats large language models, we're going to think of them as people. We should then, be able to generalize them like we would the performance of a person. But I don't think even that's really the main reason for excitement. I think the main reason for excitement is, if you just use a large language model, seemingly can generalize well past its input data. In the original Sparks of AGI paper, there are beautiful examples of an LLM producing a proof that there are infinitely many primes with every line that rhymes, and it does that, and very unlikely that that existed somewhere in the training data. So, another perspective we might take is, well, large language models can generalize well, not because they're like people, but rather because of their training process, they have uncovered some underlying structure about human knowledge, or they have constructed what people in CS might call a quote unquote world model. And what I want to briefly do for maybe like 5 minutes or so is sort of unpack what we know about whether large language models appear to exhibit world models. So I'm going to talk about very briefly 2 recent papers we worked on where we tried to formalize what this might mean and then derive its implications for how we should be conducting the evaluation of large language models or generative sequence models more broadly. So in approaching this question, we wanted to be implementation agnostic. Just think about an algorithm as a generative sequence model. It takes in some tokens and produces a probability distribution over next tokens. And by chaining that together, you can generate sequences. And the reason we want to do this, evaluate the algorithm using only its behavior, goes back to a point I made earlier on, which is that these algorithms are constantly changing and evolving over time. Being implementation agnostic, helps us focus on what's the fundamentals of the problem, not properties of the existing architecture today. So having introduced that, we now need to define what a world model could be in this world of sequences and tokens. And so in this paper, we take a very classic idea in CS theory, where we treat the world or the sequences that are produced as what is known as a deterministic finite state automata, which you should just think of this as sort of a hidden state model. There are some states that are not known to us. As we transition across states, tokens are generated, and this process of state transitions and tokens being generated produces the data that we will see. And this is a very general way we model structure in sequences. So in then tackling this problem, as I mentioned, we want to compare the behavior of the generative model to this underlying sequence data. And these DFAs provide exactly the way to do this because DFAs correspond one-to-one for what are known as regular languages in CS theory. So now we can define what it would mean for a generative sequence model to have uncovered some underlying world model, here being the DFA. And this is, a lot of math, so let me just try to unpack it a bit more slowly. So what it says is that for all states under the DFA Q, for all sequences under the DFA that would lead to a particular state, does the large language model or the generative sequence model produce the same valid continuations out of that state as are consistent with the DFA? So in other words, fix any state, consider any sequence that puts you in that state, ask what are valid continuations out of that underground truth. Does that align with what are the valid completions produced by your generative sequence model? Now, once you've applied this definition, it actually has a very clear upshot for how you should be evaluating exactly these generative models. Again, going back to very classic work in CS. And in particular, what's known as the Myhill-Nerode theorem tells us that for any DFA, any two states must have suffixes or continuations that differentiate them. So in other words, for two states to be different, they have to have different sets of valid continuations. But the challenge is, what differentiates two states could be very long. They may agree on all continuations of step 1, step 2, step 3, and only start disagreeing out to 5 steps or 4 steps, which is very different than what we do when we do next token evaluation of these models. So as a result, we can define what's known as the Myhill-Nerode boundary and then define particular evaluation metrics. But just for the sake of time, I'm going to skip ahead of how we formally define those evaluation metrics and just jump ahead to the example. So once we did all this work, we're just going to take a very stylized example to try to understand whether generative sequence models trained to do next token predictions actually uncover an underlying world model. And we took an illustrative example of the map of Manhattan. So in particular, we took a data set that has about 13 million taxi rides in Manhattan. For each of those taxi rides, we observe the starting longitude and latitude, what's the intersection the ride started at, and the stopping latitude and longitude, what's the intersection that the ride stopped at. So from this, we can then generate a large amount of sequence data where we're going to represent the sequence as first the starting location, the ending location, and then just construct paths that would go from point A to point B on the true map of Manhattan. And we constructed, 3 different types of data sets. One is where we called the Google Maps API and constructed the shortest path between point A to point B. And then also we generated a data set where the taxi just took a drunkard's walk through Manhattan, but eventually landed at the stopping point. Then once we have this data set of sequences of taxi rides in New York, we can train transformers from scratch using next token prediction. So we trained a 90 million parameter model and a model with 1.5 billion parameters. And these resulting transformers that we trained do extraordinarily well on next token prediction. So if on some held out set of sequences that they've not been trained on, we just evaluate, whether the next token generated is correct or not, they appear to do fantastically. Not only do they appear to do well fantastically on next token predictions, if you take an unseen starting and ending point, so in other words, start 2 intersections that were not in the training data, and prompt the large language model to complete the sequence, it completes the sequence. Not only is the sequence a valid route from point A to point B, but it is often the shortest path between point A and point B on the map of Manhattan, which is quite astonishing. But interestingly, even though the transformer does well on next token prediction and seemingly can solve this shortest path problem, it actually does extraordinarily poorly on this Myhill-Nerode evaluation. And in particular, it does quite badly on metrics that try to evaluate whether it acts as if it has an overly verbose state representation. And that's going to be an important point that I'll touch on at the end here. Now, why do we care about these metrics? Well, we show that not only are these metrics, just important in their own right from the theory, they actually provide guidance about how this model would generalize sort of off distribution. So one exercise we do is we can take the map of New York and insert detours. So in other words, imagine a construction site appears and you can no longer go down a particular road. Once you've introduced these sorts of counterfactual worlds that still share the same structure of the underlying state model, the transformer now does both terribly on next token prediction and can no longer find paths between routes quite systematically. Now, as just a visual way to try to represent these world model failures, we're just going to try now to visualize what is the world model that would best rationalize the sequences generated by this transformer. And to do so, we apply some graph reconstruction techniques that are given in details in the paper. So as a sanity check, if we took sort of true taxi routes on the map of Manhattan, represented exactly as the sequences I showed you earlier, our graph reconstruction techniques exactly reproduce the map structure of Manhattan. But when we do it on sequences of taxi rides generated by our trained transformers, the result is a complete mess. It contains many apparent wrong roads and flyovers that connect intersections, that actually have no direct route to connect them. And so now, what actually are we to make of this? How do we have a model that does well on next token prediction, but seems to have an inaccurate model of the world, as represented through its performance on these off-distribution counterfactuals, or in trying to implicitly represent or visualize its world model? Well, this is something, again, going to look very familiar from supervised learning circa 25 years ago. In particular, this is what we think is sort of an example of a classic and persistent problem in high-dimensional prediction, which Bryman called in the early 2000s the Rashomon effect, and in the deep learning world has been relabeled as type of underspecification. In particular, what do we mean? There are many ways in which you can perform well on some particular prediction task. But those sort of different parameter configurations that would solve the prediction task well often have many other properties on adjacent problems. And what's been building up over the last year is sort of evidence that transformers, when they are trained to do next token prediction, often build, rather than a good world model, they build a bag of shortcuts or heuristics that lead to good next token performance. So just looking at the time to make sure I have enough time to get back to sort of what's the upshot of this for applied practice, I'm just going to jump ahead to that part of the talk. But let me just pause here to see if there are any questions. Okay, so if there are no questions at this point, what is the sort of broad takeaway from this part of the talk? So the broad takeaway is, the way we understand model performance in computer science often comes from performance off these benchmark evaluations. Benchmarks are very specific sets of queries or tasks that we've evaluated large language models on. But we often want to engage in an active generalization off of these tasks or these benchmarks. The two strategies we might have for trying to do this generalization is viewing large language models like people, applying our predictions about if a person could have solved this benchmark well, surely they would be able to solve this adjacent problem well. It looks like that's not the case so far with large language models. Or we might have the view that these generative sequence models, when trained to do next token prediction or RL'd on top of that, develop not only good sequence predictions, but also good structural models of the world. And that allows them to generalize off distribution. And so far, that also appears to not be the case. So what's the upshot of this sort of summary of what we've learned over the last year? Well, let's come back to the original problem we started with, which is how can we use large language model outputs in applied research? We started by asking, well, could we approach this question of how good are LLM outputs from benchmarks? We hopefully convinced you at this point that benchmark evaluations do not directly provide the sorts of guarantees we would want. So what can we do instead? So in this last 15 minutes or so, I want to now outline sort of a different perspective we can take in applied work that would allow us to use large language models to their fullest capabilities and answer the problems we're interested in. So in particular, I want to consider a perspective on using large language models in applied work that very much sits in the line of this perspective and evaluation, where let's treat large language models as just a black box. They go from prompts to responses. And when we're thinking about whether we can use them, let's only try to introduce verifiable assumptions that the researcher can verify about how they were trained. Given their outputs, let's try to provide use case specific evaluations and then combine those two to sort of derive what might be downstream statistical guarantees we could produce. And what I hope to summarize is really a perspective that the literature has developed on prediction problems and estimation problems, and I'll try to point out sort of key papers for both of those domains as we go along. So how are we going to try to introduce large language models into an econometric framework? Well, as I mentioned, researchers often interact with them as black boxes to produce responses given prompts, abstracting away from the details of architecture, training data, and training procedures. So now let me try to formalize this notation I've been using sort of very shorthandedly throughout the slides. Now, I just want to think of a large language model as some mapping between strings or text pieces in the dataset, m hat, to some responses. And importantly, that mapping is going to be indexed by whatever data the large language model was trained on, that I'm going to denote by T. Now, in this notation, it's important to keep in the back of your minds that there are really two distinct objects that are often talked about around large language models that are being combined together. The first is what you might think of as the text generator. Once the model has been trained, how do we generate responses given any prompt string? And the second is how exactly the model was actually trained. Given some pre-training data set, some additional data set on feedback, et cetera, how do we actually go from that to the text generator that we access from some API? And importantly, we're not placing structure on how this happens. We're just treating the large language model as a black box, again, since the state of the art is constantly evolving. And then second, one thing that jumps out of this definition is the training data here, is really all encompassing. It summarizes what are all the data used for pre-training, what exactly are we doing next token prediction on? Is it, from what we crawled off the internet over the last 30 years? All data used for fine-tuning, whether that's human feedback or post-training with RLs, et cetera. So with that in mind, let's come back to these prediction problems where we have some text pieces, we'd like to predict some outcome Y, and we prompt a large language model to generate some labels Y hat. So when we then calculate the sample average loss of the large language model in our data set, can we draw conclusions about how well this outcome can be predicted by some text piece R? So to answer that question, we have to define what exactly is our inferential goal in this prediction problem. So what we do in the paper is we try to introduce sort of a thought experiment that's going to be summarized by a sampling distribution Q, which summarizes a sampling distribution over both text pieces in the researcher's dataset, summarized by D, and possible training datasets that might have been used to produce the large language model. So in other words, the sampling distribution Q is going to capture two things. One is what are the text pieces over which we would like to assess the predictability of YR? What's the population we want to generalize on? And then the second is our beliefs about what exactly was used to train this large language model. Those data sets are often hidden to us, so we need to introduce some way to model our own uncertainty about what information went into these models. Then in this context, what we would like to do is we'd like to evaluate the out-of-sample predictability of YR given these text pieces in our particular research context. So in this setup, when the researcher calculates the large language model's sample average loss on the collected data set, you can show that this is implicitly targeting the sample average loss, conditioning on whatever the large language model was trained on. But instead, we want to generalize to the performance of the fixed language model on this data set. So when are these quantities going to be different? When can we actually answer our prediction problem using an LLM? So, the first sort of punchline result, sort of stated a bit informally here, is using large language models for prediction is going to hinge on only one condition that we call no training leakage. And in particular, no training leakage can be simply summarized as the large language model cannot have been trained on the researcher's data set that we're using to evaluate predictions. More formally, training leakage has the interpretation of an omitted variables bias, where the omitted variable is the data that was used to produce the large language model, which is often unknown to the researcher. And in particular, training leakage then summarizes the extent to which language model performance co-varies with your beliefs about whether this particular text piece entered the data set.
Ashish, can
Yeah.
can I just push back on that idea a little bit just to hear your thoughts on it? So
Mhm.
this is predicated on the implicit assumption that the distribution Q that you have kind of covers, if there's overlap in the data set, obviously non-parametrically, we're covering that data set here. But you could also imagine a context in which the model is not complete in that sense, right? Like it's that distribution doesn't kind of completely cover. The example I'm thinking of is an omitted variable bias, where we can take higher order moments and use those as corrections in a measurement error type problem, right? So, and that hinges upon kind of the assumption that the correctly specified model is linear, therefore higher order moments can be used as exclusions. So similarly here, it all depends on what we believe the distribution that's covered by the language model is.
Yes.
Another
Yeah.
way of saying this is if your query, even if there's data overlap, if your query is dramatically different in some sense,
Mhm.
then now maybe there is no training leakage in that sense, in the sense that that part was never really covered in the distribution here. Just curious about your thoughts on that.
Yeah, yeah, I think it's a good question. So I would say a couple of things there. So one is, you're exactly right. The extent to which you think there's training leakage here is very much going to be a sort of statement about what do you believe the large language model was trained on, and how does that overlap or cover with respect to the documents onto which you want to generalize. And that it's interesting to maybe think about what are connections in sort of other parts of econometrics. Where we're going to go is that interpretation is easier to reason about for particular classes of large language models. Ones where, for example, they're published, you have a date on which the weights were generated and posted. Then this can be mechanically satisfied by focusing on documents after that date. And perhaps we might have the same confidence associated with, say, like knowledge cutoffs around closed-lit models, although that's still much more fuzzy. I think, the second upshot of thinking about it in that way is this all hinges on whether you want to generalize in some way onto documents that you have not yet seen, not just the ones that you've literally collected, but all documents you could have encountered under this distribution queue. And I think there are many problems where that's not true. So suppose I've just, say, collected all historical newspapers, in the 1970s. I want to use that to measure something and then plug into some linear regression. So in the estimation framework world, in the estimation framework world in general, there's a training leakage concern, but we may be willing to sort of make what you might call sort of finite population sort of statements. I'm not trying to generalize more broadly. And then lastly, I think I'll just comment on one thing that I think is not fully satisfying about how we set up this problem is I think we're taking the view that these documents are atoms. And so exactly as you said, you're really just interested in how well you cover those atoms or not. We might have a different perspective of, these documents express some type of information, and we really are worried about sort of leakage at the information level. And I think I couldn't quite figure out a way to sort of tractably model that, but I think that would be an alternative perspective on what leakage is, that I think would be important to think about. But in how we've set this up, how we're talking about training leakage is actually very familiar from the supervised learning world. Training leakage just constitutes a violation of holdouts. Now,
So actually,
yeah.
I want to clarify. So the no training leakage here. So if we have a scenario where the evaluation sample is sampled randomly from the target population, so that T and D is independent, would you say that's a case where there's no training leakage, but it is possible that the LM can be trained on the evaluation just out of randomness?
Good. So no, so that would not be a special case where training leakage is not a concern, because sort of if you only have control. So in that statement, you'd be saying like the marginal over D is independent of each other. And what matters for training leakage is what's your view on basically the correlation structure between sampling indicators for the language model's training data and what goes into your data sets. And to the extent, if you don't know what the language model has been trained on, you have no empirical control over that correlation structure. So it's really a view on how do T and D relate to each other, not just properties of D itself.
So even if D is a random sample from your evaluation population, you cannot assume that T and D are independent?
Yeah, because, well, so you could definitely write down an assumption that says T and D are independent, but Q is a statement about the joint distribution of T and D. And random sampling of D is just about the marginal in that joint. So you would need both that, you basically need to have the view that whether I've collected a data set, and maybe this would be the formal version of what you're saying. You have to have the view that whether I, the researcher, have collected a text piece carries no information for whether OpenAI collected that text piece and trained on it.
And that would be exactly the case if I were to say, I have this corpus, I'm going to sample some fraction of it for labeling by humans, and I'm going to use prediction-powered inference or design-based supervised learning to, use LLM predictions for the rest. I mean, then there's a sense in which there could be leakage. It could be that actually a bunch of my data is in the training data. But I think this is George's point. Like, that doesn't matter because it's independent of whether it's the case where I have the label, the ground truth label or not, right? Is that?
So I guess I would say, good, this is a great question. I would say it doesn't matter, but for a different reason. But it doesn't matter because I'm not trying to generalize beyond the corpus I've collected. Sort of in the PPI world, I have some corpus. I just want to make statements about sort of the finite population of documents I have. Really training leakage, the cleanest version of this would be, the cleanest example would be, suppose I am trying to do some like back testing exercise where I'm going to take headlines, I'm going to try to predict stock returns, and I'm going to use a large language model, and I'm going to back test that language model over the last 10 years. That calculation, you would, suppose you found that you could actually make a lot of money trading off the LLM's forecasts. What you would like to be able to make statements about is how well will the large language model perform starting tomorrow. So I'd like to use this back testing exercise to generalize more broadly. And in that world, even if I was, randomly picking years, the last 10 years, I would still face this concern that, well, if these headlines were in the data that OpenAI was training on, I'm going to be sort of overfitting effectively.
But just to complete that thought though, like the information versus data, or the holdout in terms of time, for example, is a good example there, right?
Yeah.
So you can imagine that, take, for example, Nielsen data sets, right? We know that there are older data sets that exist, let's say from 2000, whatever.
Yeah.
But we're not, and we know there are papers written using those data sets that the language model might have access to. So in some sense, this is kind of a worst case or a conservative way of thinking, right? Like, on the other hand, we are pretty sure that OpenAI probably doesn't have access to the actual data set. So there's possibly a subset of questions that we could ask the language model that informationally it should not have in its training information, but the possibility exists that it's there, right? Like, there's a subtle distinction between, like, I think what you're saying is that if I take the holdout view and I use like this temporal cutoff, like a look ahead bias kind of thing, yes, it's true that this data set is from a time when the OpenAI training sample happened, but we can't be sure, so we'll just be conservative in some sense.
Yeah, I think, well, good. So I think look ahead bias, I'll just briefly answer the question, then jump ahead so you can talk about estimation as well, very briefly. But I'd say look ahead bias is definitely like the cleanest version where you might be concerned about leakage, and sort of timestamping feels like a very effective solution. I think there are other problems where you might worry about leakage, but you could make a convincing, argument why I probably don't think this data has entered into the OpenAI data. So, for example, suppose I have data from like case notes from some like local government agency. I would like to use those case notes to predict something about the case. I would be comfortable saying I don't think those case notes entered into the pre-training data. And in that case, again, I'd be doing a prediction exercise from this text, but I wouldn't be worried about training leakage. But really the key is sort of to make the argument about why this is a concern or not. So I think the core challenge is, just in general, out of the box usage of LLMs, it's very difficult to enforce training leakage outside of very clear cases like look ahead bias, et cetera. Let me just briefly say, naive training leakage is a big concern in computer science on exactly the sorts of evaluations we talked about. You can do sort of closure tests using, say, this financial news headlines data set or that congressional bills application. And it seems quite convincingly that those data were used to train closed language models. And so, very specifically, I'd say ultimately for prediction problems, using LLMs requires defending this no leakage assumption. As we've sort of talked to here, for particular cases, the strongest solution is often using LLMs that have either published a training corpus or time-stamped weights. If you're in this look-ahead bias case, you can be sure that data from today is not entered into the model that you're using. And then lastly, I'll just flag, this also highlights a lot of value in researchers producing their own domain-specific language models where we have control over what has or has not entered into the data. So let me just, give I know we're basically at time. So let me give a, 1-minute summary of how we think about estimation problems. Sort of for estimation, the core problem is going to arise if there's error in the language model labels v hat for VR. As Dean sort of alluded to up front, if you naively plug in LLM estimates, you can get results that are all over the place. So all we did was we took, this was done last year. We're updating this to add GPT-5 to this week. If you prompt a large language model to label bills for policy topics and then plug those labels into various regressions a political scientist might run, you get estimates that are all over the place. The same regression can be wildly significant, but a negative coefficient, and wildly positive and significant on that same coefficient. Turns out the way to solve this problem is just building on a lot of recent work in the sort of PPI world, design-based supervised learning, where if we collect a small benchmark data set of ground truth labels, then we can robustly debias the large language model output. You can derive the familiar guarantees for debiasing. It's consistent, asymptotically normal. And if LLM outputs are accurate, they need not be perfect. This can be more precisely estimated than just if you ignore the LLM in the first place. So just to show you what happens if you debias in those same regressions, debiasing, leads to approximately unbiased estimates in finite samples for the regression coefficient you're interested in. The resulting confidence intervals from debiasing have approximately 95% coverage over all choices of models and prompt variations. And then lastly, if we compare the mean squared error of this biasing coefficient relative to ignoring the language model altogether and only reporting regressions on the validation data, you also get much more precise estimates as well. So in other words, for estimation problems, collecting validation data on a small random subset and debiasing is a generally very robust strategy that can improve inference and use LLMs to solve this text processing problem. But I see we're 5 minutes over, so let me just pause there. If you're happy to hang around for like another 10 minutes or so if there are additional questions, or also happy to keep going a little bit if folks are sticking around.